Okay, so last bit of vector stuff for this week is to look at if we can find the coordinates where two lines intersect, because we've done that in 2D before, so why not do it in 3D? So this is a little bit fiddlier, but much like in 2D, this is equivalent to doing a simultaneous equation. We want to find out where this is true and this is true. So starting at this point, moving this direction some number of stops will end up the same place we can get to starting here, moving this direction some number of steps. So for the x values, that is going to mean, from equation 1, that 3 lambda plus 2 must be equal to mu plus 5. And we'll rearrange that into a form we're used to seeing, which is the implicit form usually used for elimination in simultaneous equations. And when we look at equation y, look at the y parameter, this gives us lambda plus 8 is equal to 3 mu plus 1, and a bit of rearranging there gives us lambda take 3 mu equals negative 7. Now you could at this point plod through by hand to get simultaneous equations, but your calculators nowadays have inbuilt simultaneous equation solvers, so blah blah blah, a few steps skipped out, you will get that lambda here equals 2 and mu equals 3. So we can use those parameters in here to give ourselves the coordinates of P where these two things intersect. So from R1 we get that P is equal to 2 plus 6, y component of P is 8 plus 2, and the z component of P is negative 1 plus 8. Simplify that down and we get 8, 10 and 7. Okay, so that's the coordinate of P. Now there's no harm in checking, because that point should be the same on this line as well. So for R2 we get that P is 5 plus 3, 1 plus 9, and 13 take away 2 lots of 3 takes 6, which is 8, 10, 7. And oh look, those are the same. So they lie on both lines, which means that must be the place where those lines intersect. And they're clearly not parallel, so they're not the same line. Fantastic.